I'm going to give this a try. No notes intact with this, just going straight through the answers for the practice test for Chapter 6. Now, this was a test that I wrote, the practice test, that is. And, there are some questions on here where people asked, are these going to be on the actual test? And the answer is no. I mean, this test is to prepare you. It's not to say that this is what your test is like. It's that this is the material your test is based off of. So I really do feel like that this prepares you well. If you know how to answer these questions well, I think you know how to answer the test questions as well. So I am going to try and cut this shorter by not doing any notes alongside this. However, I still want to teach it as I go. So if I go a little longer than you need to answer these, then, then just please go ahead and skip on to the next problems. I mean, that's the benefit of this being on YouTube. So you can pause, rewind, fast forward, and do whatever you need to. Okay, for the first three problems, you're going to circle true, T for true, or F for false. And if false, I want you to correct the underlined portion below the original statement. So this underlined part will either make this true or false. And if it's, yeah, you got it. Okay, part of this is making sure that you can decipher what this says. So a polynomial's total number of real or imaginary roots, including multiplicities, is always equal to its degree. Okay, what that means is, let's say you have a polynomial, like f of x equals x cubed minus 2x squared plus 6x minus 7, whatever it is. The degree of the polynomial here is 3, because it is cubic. Okay. Now, I don't know what these solutions are. I just made this thing up. But you get some x equals something. X equals 4, and x equals plus or minus I root 7, and all this whatever stuff. The question is, will you always get 3 solutions for cubics? Will you always get 4 solutions for quartics? Will you always get 1 solution for linear? Will you always get 2 solutions for quadratics? Now count this. This is actually 1, 2, plus I root 7, and 3 minus I root 7. Now, these aren't the real numbers, but the answer to this is yes. No matter what, you always have 3 solutions. Now, they don't have to be unique. For instance, these are conjugate pairs, and imaginary solutions always have conjugate pairs. And also, for instance, let's say these were your answers. Let's say it was 4, and it was negative 5. Now, these are only 2 answers. But this whole including multiplicities part is indicating that, one of these could have a multiplicity of 2. Or you could have a cubic where your answer is just x equals 4. But what it's really saying is you have a multiplicity of 3. What you have to keep in mind is that you have 3 answers, and if you need to write them all out one by one, x equals this, like if it looks like this, you could write this out one by one, as long as you know what's going on. Because what does this look like as an equation? What if this was that? This would factor to y equals x minus 4 quantity cubed. Another way you could write this is y equals x minus 4 times x minus 4 times x minus 4. Now keep in mind, this is not that. At least I don't think it is. But there are 3 different, all multiplicity means, because I'm not going to be doing another lecture on it. All multiplicity means is there are 3 different instances where you could insert 4 for x. Here, here, and here. That's 1, 2, 3. And you could still get 0 as a solution. There's only one x-intercept, but there are 3 times in your equation where you could have plugged it in and it appears. So your answer's true. So whenever you have a cubic function, expect to get 3 solutions. Now that does not mean it crosses the x-intercept 3 times. There's a difference. Think of imaginary solutions, think of multiplicities. It can still cross once in a cubic. In a quadratic, it can cross 0 times. Okay, so those are things that you just need to make sure of that you know. You'll get solutions. You'll get as many as there are in the degree. But you have to know what those solutions mean and how they're represented. Okay, number 2. A third degree polynomial with a sum or difference of 2 cubes, factorization, can have 3 real roots. What this means is if you have an equation that's a difference of 2 cubes, like, Like that. X cubed minus 27, and you factor that, you know, you do difference of two cubes, x minus 3, x squared plus 3x plus 9, whatever. You know, this factors to this. The question is, okay, here's one of your answers, like x equals 3. The question is, can this guy ever yield two real numbers? Can this factor in a sum or difference of two cubes, can you ever do factoring or quadratic formula or completing the square and actually get real numbers, or will they always be imaginary? Now, I've told you the answer before in class, but let's go ahead and let me prove this to you for a second. Let me prove to you why I always say what my answer is. In case you don't know what it is, you're going to hear it as we go through this. Let's do, I didn't write that correctly. Let's do a cubed plus b cubed, and let's factor that. That becomes a plus b. This is sum of two cubes, by the way. A squared minus ab plus b squared. Okay, so what I'm going to do is, you know when you do quadratic formula, over 2a, what determines how many roots you have, real or imaginary, is all about the discriminant right here, this b squared minus 4ac. So let's pretend that your a squared is a, your negative ab is b, and your b squared is c. I know that looks kind of weird because we're using the same letters that we used before. But bear with me here. What is b squared minus 4ac here? If we did b squared minus 4ac, here's b squared minus 4 a, in this case is a squared, c. Now the reason why I'm using these letters is because there are numbers that would go in for these letters. So I need to make sure that you see that even if I use numbers, that the same thing will still apply. Okay, negative ab quantity squared, that's negative a squared times b squared. Negative a squared is positive. A squared, b squared, so like that. And this is minus 4a squared b squared. Ooh, can we combine like terms here? Absolutely. This is 1a squared minus 4a squared b squared. That's negative 3a squared b squared. Okay, what did I just find? This is your discriminant. This is the discriminant inside what gets factored in this portion right here. Now that's a negative 3 right there. Does that mean that this whole thing is always negative? Well, I want you to think about some values. What if we used a number here for a, and we squared it? What would happen? Hopefully your answer is it would become positive. What if you used a number here for b, and you squared it? What would happen? And again, your answer is it would become positive. So negative 3 times a positive number times a positive number is a negative number. So here's your proof. Your discriminant will always, let me repeat that. Your discriminant will always be negative. It will always, always, always be negative in this scenario. There's nothing that you could ever do where your square root would not be negative. I'll give you one exception to that, and that's if one of these are 0. If that's 0, then that means you're not looking at a third degree polynomial with its sum difference of two cubes factorization. So there's that. Now, somebody else might jump in and say, wait, Mr. Robinson, I can think of a scenario when I square a number and I make it negative. You know what it's called? It's called an imaginary number. What if we squared, I squared. I squared is negative 1, and say this was a real number. Oh, suddenly it's positive. You're like, oh, Mr. Robinson, look, I just got a positive discriminant out of that. And I say, well, yeah, but you know what you just used? An imaginary number, which means this guy had an imaginary coefficient or constant, which means you're going to have imaginary roots. Because your A, your B, or your C is imaginary. So that doesn't much help you. So this guy right here will always be, excuse me, get out of my way. So just out of my computer. All right. So this guy will always be negative. Not only that, but you know, you could actually use this in your discriminant for your answers. Here, let's do an example. Let's do that x cubed minus 27 again. Okay, so that's x minus 3 times x squared plus 3x plus 9. Okay, so here's x equals 3. Now in this one, you could do x equals negative 3 plus or minus the square root. Instead of doing b squared minus 4ac, you could do negative 3 times a squared, that's 1, times b squared, that's, no, b squared is 3, 9. So, no, I'm sorry, yeah, your b is 3. So b squared is 9. Negative 3 times 9 is negative 27. See, I didn't have to do the discriminant there. I didn't have to do b squared minus 4ac. This thing does it for me. Kind of cool. And then yada, yada, yada. But again, your square root's always negative. So what's the answer to this? Because we just went through all that? Well, the answer is false. You can't have 3 real roots because you will always have 2 imaginary roots. Let's correct this statement as we're supposed to. Okay. And this is actually on an answer key here. You'll have 1 real root and 2 imaginary roots. Those 2 imaginary roots will be a complex conjugate pair. Okay. Always. So you might have noticed that, remember, this is replacing this part here. To make it true, it would say this. A third-degree polynomial with sum or difference of 2 cubes factorization will have 1 real root, 2 imaginary roots, always. Complex conjugate pair, remember, it'll always come in that plus or minus, 2i, or whatever form. Okay? It'll always be plus or minus for that. Okay, number 3. A cubic's polynomial domain and range are both all real numbers, always. I want you to think about any cubic number you've ever seen. Any cubic polynomial. What does it always look like? Oh, yeah, sure, it could look like that. It could look like that. It could look like that. I'm kind of singing. Point is, what always happens, no matter what, in the x direction for your domain, can it go from negative infinity to positive infinity and always get a y value? Uh-huh. In fact, all of these polynomials are normally considered functions, so you should assume that that's going to happen anyway. Yes, its domain, all real numbers. Its range, ooh. I want you to think, I'm going to erase the cubic for a second. What if I made this quadratic? Domain would be all real numbers. It can span left and right forever. Range, look, this thing's got a vertex. It starts up, stays up, or starts down, stays down. And there might be information that it's missing, right? It might not come up here, or, there's some places it might not hit. A cubic's different. An odd degree polynomial is different. It starts from the bottom and finishes up. Or it starts from the top and finishes down, which means it spans the entire range of y. It'll never stop going to positive infinity and negative infinity. So it is true. It is true that a cubic polynomial's domain and range are both all real numbers always. There's no way around that. The cubic will always go all the way left to right and up to down. Okay, number 4. Match the following graphs with each of the cubic equations below with its letter. Justify your decision. So we have equations. We want to say, oh, is this letter A, B, C, or D, etc., etc. So let's go ahead and justify these here. Let's take a look at this equation and say, what should the graph look like if we have this? Well, first of all of these are cubic, so there's no denying anything there. You can't play process of elimination that way. If I did expand this would be a positive x cubed. So one thing for sure is we know that it's either going to be A, C, or D. It can't be B. And in fact, let's figure out which one should be B. Oh, it's the one with the negative coefficient. I already know that one's B, for example. If you want me to explain that, we sure will. We're going to justify each of these. It's a positive x cubed. If you know something else about this is that it's already in factored form. And what that helps you do is it helps you see 2 things. One, helps you find your roots. The only problem about this is that, none of these are numbered. But it does tell you, hey, this is a positive root. This is a positive root. How many of these have 2 positive roots? This one doesn't matter. This one has 1. This one has 1. This one has 2. This is the only one with 2 positive roots here. Not only that, but probably the most important thing that you can see out of this is this little squared guy. And that's all about multiplicity. This thing has a multiplicity of 2 at x equals 1, at the leftmost x-intercept right there, the leftmost root. I'm assuming that's x equals 1 because this is the only one they could cross by, which means it bounces back right at that point there. Like I said, I wanted to do more notes on bounce back stuff so you could see that. I don't think I'll have the time here. So this is the one that applies for that, so that's going to be A. Let's write a good justification for that. Let me cross that out now. Why is it A? Well, both roots are positive. Okay. And also, there's a bounce back that exists at the leftmost root. Presumably that's x equals 1. Right, we got to make that assumption perhaps, so there's that one right there. A is justified. Okay, let's talk about B, because I think we already figured that one out. Really, the only thing I should have to say is, hey, negative cubic coefficient, or whatever. The other thing you can do to justify this is that it's the only one with a positive y-intercept. Look at this plus 8 right there. The constant value is also the value for y when x equals 0. Plug in 0 for x, you get 8 for y. I don't know if I know that's 8, but I do know that it's the only one that crosses through in the positive y-intercept. So another thing we could say here after we cross out B is that there's a negative coefficient in the cubic term, and there's a positive y-intercept. So, 2 down, 2 to go. All right, here we go. Oh boy, what is that equation there? Y equals x cubed plus x squared minus 6x. A couple things you can check out here. First of all, there's no y-intercept. Well, I'm sorry, your y-intercept is 0. It's not visible, however. Okay. So you're taking a look at both of these, and you're saying, well, which one has a y-intercept of 0? Well, it looks like a D does. You can already justify it just by saying that right there. So I already know this is D. How else can I say that it's D? Let's take a look a little further. This has a common factor of x. If I factor this out, I mean, I could keep going. We're trying to save you from doing the math or creating a table, but having a common factor of x makes you know that x equals 0 is one of your roots, which is the same thing about the 0 y-intercept. If x equals 0, then y equals 0, and vice versa. That means that your graph passes through the origin. So those two hints kind of indicate to you, yeah, this one's got to be that right there. So this one is D. Let's justify D. Common factor of x and a y-intercept of 0. Kind of the same thing, if you think about it. They both mean it passes through the origin. The last one must be C. It's by process of elimination for us, but let's come up with some good reasons. X cubed minus 8. Okay, negative y-intercept. Aha, passes through there. This one had a negative y-intercept. You're like, oh, well, hang on a second now. How come this one is, yeah. Well, what else is this? What can you recognize that as? It's a cubic. There are two terms, the constant and the cubic term. They're both perfect cubes. This is a difference of 2 cubes. This becomes x minus 2 times x squared plus 2x plus 4. Well, there's one real solution, and this one, I don't think I need to give reasons for it anymore. We spent a whole, at least 5 minutes talking about it, number one, or whatever. This has 2 imaginary solutions. Whatever they are, it's x equals plus or minus I something, or whatever. I'm not saying that's your answer. I'm saying that you know they're imaginary. This thing only crosses the x-axis once. How come? It's a cubic. Isn't it supposed to cross through 3 times, Mr. Robinson? Well, no. It's supposed to have 3 solutions. It needs to cross through the x-axis at least once and at most 3 times. If it crosses through once, that either means it has a multiplicity of 3 right at the origin, like that, or if it passes anywhere else, that means you have some imaginary solutions to take care of. So, this is C. For what reasons? You have 1 real root, only 2 imaginary, which makes sense, that adds up to 3, and you have a negative y-intercept. Sorry, my head's kind of feeling its thing right now. Oh boy. Okay, so that was all of number 4. Okay, number 5 through 7. This should say 5, 6, 7. Sorry. I pasted these over, so that's going to have that issue. Okay, what am I? So I got a little creative with these when I was making clues and stuff. I wanted to have fun with it. I want you to know that you know what the words mean and you know how they exist and all that. So, yeah, to me these problems are kind of fun. And if you know what all these things mean, then I think you'll have no trouble anyway. Okay, each problem contains a series of clues for you to classify each polynomial by its degree and number of terms. So these guys represent the degree. Either it's a linear, quadratic, cubic, or quartic, meaning x, x squared, x cubed, or x to the fourth. These are number of terms. Monomial is one term, binomial 2, trinomial 3, four-term polynomial, hey, 4. Enough said. Couple other things that you can probably keep in mind as you do this. All of these, a linear, quadratic, cubic, and quartic, they can all have one term, right? You can have like y equals negative 2x squared. That's a quadratic monomial, right? So you can have that. It's not unheard of. These do have maximum amounts of terms that you can have, though. A linear term can only have 2 at most, right? If you think about this, this is like ax plus b. This can have ax squared plus bx plus c. It can have 3 terms at most. This can have 4. And this can have 5. bx cubed plus cx squared plus dx plus e. So it's probably important to say, well, I know I can never have a linear trinomial, right? It's impossible to have. You can't have 3 terms in a linear function. So you can already weed some things out. The only other thing that helps you out is no terms will be repeated. So although we're not going to use all 8 of them, you know that you will use at least 6. You'll be using 6 unique ones as we go through. So maybe you know that one of these is right, and you can move along from there. Why am I saying all this? Because I'm helping you take a test well. You read the directions, you say in your head what things mean and what they don't. Okay, let's get started. Number 1, I have 2 terms. Hard to get any more obvious than that. This must be a binomial. What kind of binomial? Okay, now, one thing you know for sure also, I need to make sure you understand this. If this is binomial, then we're not going to use binomial again. No terms will be repeated. So you know none of these answers will be binomial. Again, I'm simply helping you out not just on the material, but on test taking. If I divide a linear factor out, I become quadratic. Okay, quadratic means it's an x squared thing. I'm not saying this is x squared. It's saying if I divide a linear factor out, I become quadratic. So what divided by a linear guy is quadratic? Well, you basically lower 1 degree. If I divide by x, that means I was 1 degree higher. So not quadratic, but cubic. So this is a cubic binomial. Okay. So that's what that thing's called, a cubic binomial. It's 2 terms, just like x cubed minus 8, or, like whatever the thing was, cubic binomial. There you go. If I divide a linear term out, it becomes a quadratic. Just like over here when we did I write it? Like right here. If I divide this linear term out, it becomes quadratic. I'm not saying it becomes a quadratic binomial. I'm just saying it becomes quadratic. It's the degree. Okay, number 2. My degree and number of terms are the same amount. Okay, degree means what your highest degree is, what power it raises to. So linear means to the first power. It's a degree of 1. Quadratic is degree of 2. Cubic is degree of 3. Quartic is degree of 4. Now, here's another good test-taking strategy. Check this out. If the degree and number of terms are the same amount, and if we've already used binomial, that means your answer couldn't possibly be quadratic binomial. Why not? Well, because no terms will ever be repeated. We are not going to repeat binomial again, so you know it's not going to be quadratic binomial. So you know it's not quadratic, and you know it's not cubic trinomial because you can't use cubic either. So we know your answer is either linear monomial or quartic 4-term polynomial. Okay? Because if the degree and number of terms are the same, it's either 1 degree, 1 term, 2 degrees, 2 terms, 3, 3, and 4, 4. Couldn't be either of these because 2 of these have already been used. If I have 2 real roots, okay, automatically you know it's not linear monomial. Linear term can only have one real root, period. Anyway, so you know it's going to be quartic 4-term polynomial, but let's talk about this and make sure you get it. I have two real roots, but one of them has a multiplicity of 3. So let's give an example. Let's say you had x equals 1 and x equals 4. Let's say that x equals 1 had a, shouldn't write had a multiplicity of 3. That means your equation would look like y equals x minus 1 quantity cubed times x minus 4. Okay, this is quartic. If I expand, it looks cubic right there, but if I expand this thing completely, there are my two real roots, 1 multiplicity of 3, blah, blah, blah. This would be y equals x to the 4th, blah, 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 then plus 4 at the end. No, plus 4 at the end. But this is a quartic. And I'm not saying that this thing gives you 4 terms. I'm saying, let's say, for example, blah, blah, blah. I'm sure I could find a way to make that have 4 terms instead of 5, but I'm not going to do it for that one. This one becomes a quartic 4-term polynomial. Okay. Now this one's the kind of the most riddle-like. I crossed through the origin and nowhere else. My range is limited, so they call me a square. I am forever alone. Forever alone, look that up on Google. That's a meme. You should know what that is. That's why I did it. Did it for the lulz. Okay. Let's say you have a graph here. There is kind of a giveaway here. And to be honest, I didn't even think about it beforehand. I didn't need the forever alone thing if I really thought about this. Let's do a linear graph that crosses through the origin. What would that equation be? It would be y equals something x, whatever the slope is. Let's say it's 1/2 x. Is there a y-intercept? No, because there's no vertical shift. It crosses through at 0. It's plus 0. Let's try another one. Let's try a quadratic that crosses through the origin nowhere else. Okay, well, this could be y equals 2x squared, whatever it is. Could there be a plus 4x right here? Could there be a plus 7 or what? Well, there definitely couldn't be a constant. Remember this. There could not possibly be a constant. If there was, that would mean that it is not on the origin. It would have a different y-intercept. Well, could it have this? What would happen? You'd factor that out. You'd say x plus 2. Oh, look, I have 2 different places where it crosses, not in the origin. So something that you know about this thing for sure is that it has to be a monomial. I mean, I could do this with cubic and quartic as well. If this was x cubed, right? If this was something x cubed and it goes through here. If I have anything else in here, anything else, first of all, it can't be a constant for the very reason I said. If it was a constant, your y-intercept would not be in the origin. And it couldn't pass through here like that, otherwise it wouldn't be a function. So it has to have an x in it. And if it has to have an x in it, that means x is a common factor. And if x is a common factor, then that means it's crossing through multiple different places, not just the origin. So it can't do that. So there's something behind that that says it must be a monomial. Now, you only have one of a couple options anyway. Let's see, what did we cross out these? It was either trinomial or monomial anyway. And I don't think there's anything that was restricting this to be linear yet. So this has to be a monomial. Okay. Now, the real giveaway for that was forever alone. But again, I want you to really take home the things that I'm saying here. All of these things matter. All of these things matter. Because if you talk through the stuff, then you really understand the material in a certain way. My range is limited. Range. Now before I was trying to make some jokes like, oh, you have less range than Taylor Swift, stuff like that. Or even though you have more range than Taylor Swift, it's still limited. Whatever I was coming up with. My range is limited, so they call me a square. Square like a loser, whatever else. Square. When do we use square? You think about x squared, square, quadratic. That's what I was going for. Even if you didn't know it. You're between quadratic and linear. Linear's range is all real numbers. Linear's range, like a cubic, like a quintic, if they call it that. Anything with an odd degree, they are all real numbers. This thing goes from negative infinity to positive infinity. Quadratics and quartics, they have vertexes. They have minimum points. Quadratic stops somewhere. It has a vertex. Its range is limited. Doesn't matter if you know whether that's a square or not. It can't be quartic or cubic. We already used them. So it must be quadratic, and we said it must be a monomial. So this is a quadratic monomial. And I am forever alone. Okay, numbers 8 and 9. Graph the following polynomials. Make sure to scale your axes and include both x and y intercepts. Well, first I'll also label these x, y, x, y. I know I didn't do that on your paper. I'm sorry. I don't even think I put arrows. All right. Include both x and y intercepts. So, here we go. Y-intercept here is 0. I already know that one. This one's 4. It might be good to write that before I forget. Y-intercept here is 4. Y-intercept is here's 0. Okay. Now, graphing these things. We graph cubics a little bit abstractly, meaning we don't really know too much about the relative maximum, relative minimum. That's more solved through, calculus or whatever else. Or if you have a graphing calculator, you can do that too. We're not too concerned about that. We're concerned about knowing its behavior, whether it goes this way or that way, based on whether your coefficient's positive or negative. We know it'll go this way, meaning start from bottom, finish at top. We also need to find x-intercepts, imaginary solutions, if there, and if there are any multiplicities that exist. So let's get to work. There are only 3 different ways that you are going to be provided a cubic value and be expected to know how to solve for x. One way is this one, which is common factor of x, at least of x. So that's one way. I'll give you the other 2 because you're going to run into them. Another way is sum or difference of 2 cubes. Okay, because you can factor that. Basically, the idea is, can we get these down to a quadratic somehow? The third way is if you have none of these, and if, say you had a constant here, let's say it was 6. It's like, well, what do we do with that? There's nothing called rational root theorem. We didn't learn it, so we're not going to do it. It is if you are given a root. Now, the rational root theorem is exactly that. You find one of the roots, and then you divide out. And what do? Yeah, you use polynomial division or synthetic division to figure that out. So those are the 3 ways you'll do that. This one's a common factor version. X is a common factor. Let's go ahead and get her done. Let's divide by 2x, or divide 2x out. You have x squared plus 6x plus 8. So, quadratic here, the 2 numbers that multiply to 8 and add to 6 are positive 4 and positive 2. So, if you want to find your x-intercepts, your zeros, you got to set that equal to 0. Zero product property says 0, negative 2, and negative 4. I really should write these as negative 2, 0, 0, 0, and 4, 0, negative 4, 0. Those are your x-intercepts. Your y-intercept is 0, 0. I need these points all plotted right here. So to scale this, let's at least go to negative 4 right there. It's 4 and negative 4. Okay, and let's go ahead and graph this. I already know my values. You should know them too. So our y-intercept was 0. We had negative 2 and negative 4. The behavior of this guy is such that it starts from the bottom. It's going to cross through, multiplicity of 1. Going to hit here, go back down, and go back up. There you go. There's your graph. Y equals 2x cubed plus 12x squared plus 16x. Okay, number 9. We already have our y-intercept right there. You write that again as it's supposed to be 0, 4. So we know there's a 1, 2, 3, 4. If that's 5, then there's 1 point. Okay. Here's a quartic. Now, this quartic is unique in a certain way. You're like, okay, I don't know how to factor this. And then I said, well, you know what? Do you know how to factor this? And you're like, oh, sure, yeah, that's a quadratic. I got to find what 2D, blah, blah, blah. Yeah, so the thing is, quartics, and not just quartics. This can be anything. This could be a cubic, this could be x to the 6th minus 5x cubed plus 4. This could be x to the 8th minus 5x to the 4th plus 4. There's a common pattern among these, even for x squared, just like I had before. And it is that you have a term in the middle, and it is directly in between your highest degree and your lowest degree. In this case, your constant. These are all x to the 0 power, if you didn't know that. A constant is x to the 0 power. Add 4 to get to this degree, add 4 to get to this degree. Add 3, add 3. Add 2, add 2, add 1, add 1. So the thing is, you can make what I guess you'd call a direct substitution here. I could actually go into this quartic and say, what if I wanted to make this look like a quadratic? I wanted to say instead that this is x squared, quantity squared. X to the 4th is that. I'm going to make everything be an x squared instead of an x, and that's the point. Instead of these being x to the 1st power, let's make these x squareds. 5x squared to the 1st power plus 4. So one intermediate step you could do, if this still looks confusing to you, is you could put in another variable. Like I use a all the time. Let's let a equal x squared, and we're going to do direct substitution here. That'll be a squared minus 5a plus 4, because again, you know how to do that. This is something that you're going to see a lot when you do what's called integration in calculus. Not integrated math, but when you go into calculus and you do integration, you're going to need to use letters. I think you're going to use the letter U a lot, and you're going to do that to help you integrate. There'll be good reasons for it, and you're going to say, "Oh yeah, Mr. Robinson told me that." When you actually do it. Okay, how does this factor? That's y equals a minus 4 times a minus 1. Okay. And now the thing is, our guys weren't a's; they were x squared. So we got to bring that x squared back. It was just there to help us figure out how to factor that. Okay. Now we're at this right here. What are we trying to do? We're trying to find x-intercepts. Well, hey, these are quadratics. They are factorable. Also, by the way, you could go straight into this whole x squared equals 4 and all that business. There are things you have to be careful of. Make sure you don't just write x equals 2. It would be plus or minus 2. Also, you have to make sure that if there's a question that asks you to factor this down completely, you know how to do it. So I might as well do this for you. Hang on, I gotta not talk for a second. It's my head. Okay, here. I'm just gonna start writing these. So there are 4 x-intercepts right there. Negative 2 and 2, negative 1 and 1. You have a y-intercept of 0, 4. So let's graph this. Okay, here we go. This is a quartic function, which means, and it's positive, which means it starts from top, finishes on top. So it'll come through here, no multiplicities, hit through there, come back up and go, hello, I need to hit my y-intercept, don't forget that guy. It's going to come back down all symmetric and it's going to come back up and there's that W shape that y'all yearn. And that happens because it hits 4 different x-intercepts right there. So there's your graph. I should have actually scaled this and that. I should have written some numbers there. This should be a 2 and a negative 2. Negative 1 and a 1. There we go. And we're good to go. There's your graph. Okay. As it turns out, I don't think this will be any quicker than any of my other things. I'm only halfway through this. You know, as you say, I talk too much. I'm trying to help you, though. Okay. Number 10. Factor and solve. Okay, I'm going to deviate here for a second. Let's do, what if this said 8x squared equals 25, for example? One way you could do this, by the way, is you could divide by 8. Oh, you know what? I don't want to use 8. That's not a perfect square. Let's use 9. You could divide by 9. And then you could take the square root of both sides. And x equals plus or minus the square root of 25 over 9, which is plus or minus square root of 25 over square root of 9, which is plus or minus 5 over 3. Not bad. Now, the thing about this is you have to remember the plus or minus because then you know you have 2 solutions. And it makes sense because it's a quadratic. It should have 2 solutions. You can't do this with cubic. Someone's like, well, Mr. Robinson, why not? Here's what would happen if you tried this with a cubic. Divide by 8. Take the cube root. That's the cube root. By the way, we're doing this next chapter, so brace yourself. Cube root of 27 over cube root of 8. So x equals 3 over 2. blah, 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 blah. Now, two things here. First of all, you might say, why didn't I put plus or minus? Well, because this isn't, because negative 3 halves cubed is negative 27 over 8. It's not positive 27 over 8. So it's not plus or minus. It's just the positive version if it's positive. If this was negative, then it would have been negative. Second thing is, look, there's nothing wrong with this answer. This is a correct answer. In fact, it's the only real root. That's the thing about imaginaries, is they're not always accounted for. This is a cubic. Hint, how many solutions should there be? I'm expecting 3 solutions, or 3 roots, or whatever. This is 1. I didn't get all 3. This is an improper way of going about this problem. By and large, it got you one of your roots, and there are other ways you can get your other ones with that. I could have done synthetic division from there and gotten my other ones. But here's the way I'm going to do it. I'm going to subtract 27. Recognize that this is a difference of 2 cubes problem. This is 2x quantity cubed minus 3 quantity cubed. That's equal to 0. Factor time. 2x minus 3 times, I'm going to write this out so you for sure know what to do here. 2x squared plus 2x times 3 plus 3 squared equals 0. So this is 2x minus 3 times, here we go, 2x quantity squared is 4x squared plus 6x plus 9 equals 0. Okay, now that I've exhausted all that, I'm going to put this up on top. Now that I have that, we'll go ahead and finish this off here. Finish it like a chocolate cake. So if these are equal to 0, either 2x minus 3 equals 0, in which case 2x equals 3, and x equals 3 halves. Hey, we already had that answer. Cool. Yeah, but there were 2 other answers right here. 4x squared plus 6x plus 9 equals 0. What did we say about these? Non-factorable and non-real. These are 2 imaginary solutions. Let's use quadratic formula. We could do b squared minus 4ac. That would be a 4. b squared minus 4ac to find the discriminant first. I also know it's negative 3 a squared. What was it? B squared? Oh, I'm sorry. Your a value is from a cubed minus b cubed. So negative 3 a squared b squared. I don't know if I did that right. So that would be negative 12 times 9. That's negative 108. So let's see if we get negative 108 doing it this way. I was just testing my theory that negative 3a squared b squared works. 16 times 9 is negative 144, so it's 144. That gives you negative 108. So what do I need that for? Well, discriminant time. Quadratic formula time. X equals negative b plus or minus the square root. Here's your b squared minus 4ac all over 2a. So it's negative 6 plus or minus. Here we go. It's 36 square root of 36, 6i root 3 all over 8. You can divide here. Divide everything by 2. Negative 3 plus or minus 3i root 3 all over 4. So your 3 solutions are 3 halves, negative 3 plus 3i root 3 over 4, and negative 3 minus 3i root 3 over 4. That's an I, by the way, not a 30. I curve a little too much up there. Okay, so please pause that if you need to write that down, because I'm going to erase it. Get out of here. Okay, number 11. Okay, before you begin, how many solutions should there be? This is a quintic. There should be 5. We haven't dealt with quintics very much, so you might want to say, there's probably something different about this problem. Yes, indeed there is. Common factor. Find it. When in doubt, search for a common factor first. In fact, 3x can come out of here. You got x to the 4th plus x squared minus 20. That equals 0. All right, this is like that other quartic problem. You want to do that let A stuff, whatever. If you want to practice that, go ahead. I'm going to go ahead and write the next step. I want to make sure I taught it once. I don't want to overdo this as far as time goes, because I know that this, I'm already probably pushing an hour here. Okay, so I want to make sure that I keep going as much as I can. So this is what this factors to. Okay, now this factors to x plus 2x minus 2. This is a difference of two squares, like that other problem earlier. So, either 3x equals 0, so x equals 0, or x equals negative 2, x equals positive 2. You really have to put the plus. Should be two more solutions, right? Here are three of them. It's in the quadratic. X squared plus 5 equals 0. So x squared equals negative 5, or x equals plus or minus I root 5. That's the square root of negative 5. So, I have 1, 2, 3, 4, 5 solutions. There they are. In this quintic function, I think that's what it's called, 3 times it crosses the x-axis. There are two imaginary solutions. You're good to go. And there's that one right there. We gotta someday try plugging these in so I can really show you what happens when you raise it to the 5th power and all that stuff that it does. I think that'll be good times. Okay, number 12. 12 and 13 are, gotta do a little bit more. I'm going to make sure that, you know what, because I don't know if that long division thing will come out here. I'm going to show it both ways. I'll show long division and synthetic division. So what you have to do here is when it tells you x plus 8 is a factor, what that means is you can divide this by x plus 8 and you'll get a number out. It's like if I give you the number, 64, and then I say, God, what are factors of 64? If I say 16 is a factor, what that means is you can divide this number by 16 and get a number, which would be 4. So the same thing here. We can divide this by this. And then you get a quadratic, which hopefully is factorable, and then you're good the rest of the way. And if not, quadratic formula. So I'm going to do long division first and synthetic division second. I'm actually going to do it for both problems, this one and the one afterward. That's kind of what takes up time on this thing. Okay, in long division, you take your most significant term here, your x, and you compare it to all the guys that you're going to, compare it to. You say, okay, how many times does x go into x cubed? Meaning x times what number is x cubed? It's x squared. Now if I get my notes up, my video notes up for this, you'll see exactly kind of what I did here. X times x squared is x cubed. 8 times x squared is 8x squared. You subtract. These should always cancel. Always, always, always. That was the whole point of that. You want to get rid of the cubes and go down to quadratics. Subtract here, you get negative 6x squared. Bring down the minus 39x. Get x plus 8. X goes into negative 6x squared minus 6x times. Multiply. It's minus 48x. You got to subtract a negative here. So this becomes positive 9x. It's plus 72. Remember, I wrote this problem. I wouldn't have made it so weird that it has such a weird remainder. In fact, this doesn't have a remainder. And you get 0. So, this would be the result of dividing it. This is not your answer. It's the objective. Factor and solve. Factor is the first objective here. What is this factor to? Well, x cubed plus 2x squared minus 39x plus 72 is also x plus 8 times x squared minus 6x plus 9. Remember, we divided this from this to get this. So this times this equals this. So let's rewrite this as x plus 8 times x squared minus 6x plus 9 equals 0. Okay, better hope this is factorable. Oh yeah, of course it is. X plus 8 times x minus 3 times x minus 3 equals 0. So what are your x values? Either x equals negative 8, x equals 3, or x equals 3. Now, doesn't that look weird to write x equals 3 twice? Of course it does, but if you have to make sure that you know how many answers there should be, we should have had 3. We got 3. What most people will do, especially because you're supposed to, state the multiplicities of roots if they exist. You'd write x equals 3 once. Then you'd tell your grader, or whomever you're talking to, that x equals 3 has a multiplicity of 2. That's your final answer there. So these are 3 solutions. This appears twice. Okay. Now, I promised synthetic division. It's probably quicker. Synthetic division. I'm going to erase this, so make sure you pause it if you want to write anything down there. Synthetic division is very nice. I'm not going to explain how it works compared to long division. I've done that a lot. But what you need for synthetic division is a linear factor. You need something in the form x minus a. In this case, this is x minus negative 8. Because your root is a. If x equals a, your root here is x equals negative 8. This is your root. This is the number you need for synthetic division. What it does is it allows you to use addition, and it allows you to ignore all the extra x's. So we're going to use negative 8 as our root here. Now I'm only going to do the synthetic division part. I'm not going to do the factoring again. You'll get to the same factoring answer. Let's list our coefficients. 1, 2, negative 39, and 72. The one regret I have on this test is that I did not put any zero placeholder questions where you had to make sure you put in a zero somewhere. So I'm sorry about that. Bring down the 1. Negative 8 times 1 is negative 8. 2 times negative 8 is negative 6. Negative 8 times 6, negative 6 is 48. Negative 39 plus 48 and 8 is 9. Negative 8 times 9 is negative 72. Negative 72 minus 72 is 0. This is your remainder. Working up from there, this is your constant. This is your linear term. What just happened? Sorry about that. This is your linear term. This is your quadratic term. X squared minus 6x plus 9. And that's the same answer. And you keep going from there as we went last time. Okay. Now something tells me that way was probably quicker. Okay, number 13. I'm going to do this two different ways. X to the fourth plus 8x cubed plus 9x squared minus 38x minus 40 equals 0. 2 and negative 4 are roots. So you can do this one of two ways. Let's go the long and tedious long division way first. Now, if these are both roots, let me go back to that 64 example again. Yeah, you have 64. What if I said, 2 and 4 are roots? And you wanted to, keep breaking down this number. I would do 64 over 2. And would I do 64 over 4 after that? No, I take 64 over 2, get what that number is, then I take that number and divide it by 4 and see what I have left. So make sure that if you do division twice, you divide by it once, then you take that quotient, and then you make it your dividend, or whatever it is, divisor dividend, your dividend. And then you divide it by the other number. Okay? Another way you could do it, and this is how I'm about to do it, instead of 64 over 2 and then 32 over 4, if these are both roots, then why do you write divided by 2 then divided by 4? Just do it divided by 2 times 4. That's 64 divided by 8, buddy, which is 8. So what I'm going to do is long division. And when I do, I'm not going to do divided by x minus 2. This is x minus 2, by the way, this factor. And this one's x plus 4. Why divide it by them individually when I could combine them as one mega, super quadratic factor here? If 2 and negative 4 are roots, then you can divide this by x squared plus 2x minus 8. Now, as I'm saying that, I have a grin on my face. I'm going to have fun with this one. I better not screw up, and you better not screw up. Remember, I wouldn't do this if it had some large remainder. I wouldn't give that to you, especially when you're trying to solve for x, or solve for your zeros here. That would just be mean. It's important, though, because now you know, okay, here's something that long division can do that synthetic can't. You can divide quadratics. You can do it with synthetic division. You just need to get your linear factors. Okay, how many times does x squared go into x to the fourth? So here we go. Got x squared times. You got to multiply all three of these here. You got x to the fourth plus 2x cubed minus 8x squared. Now remember, I'm going to subtract 0, 6x cubed, 17x squared. Subtracting and negatives adding. I got to bring down one more term here because I'm going to have to combine, three terms down here. So x squared plus 2x minus 8. X squared goes into 6x cubed. 6x times. That's 6x cubed plus 12x squared minus 48x. Subtract 0. 5x squared. 10x minus 40. Bringing that down. X squared goes into 5x squared 5 times. You get 5x squared plus 10x Let me guess. Oh, minus 40. Subtract, you get 0. Nice remainder. This time I'm going to hold off. I'm not yet done with the problem. I'm going to stop at this point, make sure we got this answer. I'm not going to erase it. And on the other side, I'm going to do synthetic division. And you can see and decide which one you prefer. I'm sure synthetic's probably the easier way here, especially because they gave you the roots. I should have given you that x squared stuff, made you factor, and then go on your way. Remember, this was a challenge problem. Okay, if 2 and negative 4 are your roots, you're going to do synthetic division. Do one at a time. Let me separate this here. Let's do 2 first. Now, I have 1, 8, 9, negative 38, and negative 40. Okay? 1, 2, and if you're okay with me just kind of writing this, I'm not going to say everything I do. It's kind of exhausting. Okay. What I did was I created a cubic function. Remember, remainder, constant. So right now, and I'm going to erase this. I'm not going to keep it up here. Constant, linear, quadratic, cubic. Okay. What I'm going to do next, and remember, I am going to erase this, but what I'm going to do next is divide this then by x plus 4. Or, use negative 4 as my new root and divide this one out using synthetic division as well. You could use long division at this point. Doesn't matter. You could do one and the other. But I'm going to stick with synthetic for you. Now, why am I erasing this? Because why rewrite this when I already have it right here? I have these numbers. I might as well work with them. So here I have negative 4. Let's do synthetic division one more time. 1, negative 4, 6, negative 24, 5, negative 20, 0. Aha! 1, 6, 5. 1, 6, 5. That is x squared plus 6x plus 5. So we divided. I divided both ways here. I did long division and synthetic division. Which one do you prefer? Most prefer synthetic. I ain't hating on long. Synthetic does have some hiccups there. There are some things behind doing it that make it harder. Trust me. These aren't necessarily the problems that set you up for that. Okay, so what did we do? We have to solve for x still. This whole thing, now remember, 2 of our factors are x, what were they? X minus 2 and x plus 4. You multiply those. You multiply it with x squared plus 6x plus 5. This together is the same thing as x to the 4th plus 8, all that. Now this we rewrote as this factor. That equals 0. Keep factoring if you can. I think you can. I wouldn't have made the problem that way otherwise. X plus 5 times x plus 1. All right, we're in business. If these equal 0, x equals 2, negative 4, negative 5, and negative 1. Cha. Are those all the answers? We have 4 of them. Was this a quartic? Oh yeah. Quartic function, 4 answers, real numbers, integers. They look good. We found 2 different ways to get to that division too. All right. Let's finish this off. We got 4 more problems. Now these ones, there's some challenge right here, but oh, we got linear again. Do you remember how to do that? Aha, see? We're trying to make sure that you're still ready for your final. X-intercept, or intercepts. You can't really have multiple here unless it was a horizontal line. Negative 6, 0. Y-intercept, 0, negative 3. Oh, by the way, what we're going to do is eventually we're going to write things in standard form. That goes all the way down here. Meanwhile, find the other requested info along the way, because it'll help you. Slope-intercept form. Do you guys remember that? Yeah, that's y equals mx plus b. We need to find the slope. We have the y-intercept. It's right there. So it's y equals something, x minus 3. What's its slope? Down 3 over 6. It's negative 3/6. It's negative 1/2. Negative 1/2 x minus 3. Slope-intercept form? Standard form. The way I do standard form is ax plus by equals c. Having the constant on one side, your x and your y on the other side. No fractions. And hopefully positive a value. Let's add 1/2 x over to the other side. No fractions. Multiply both sides by 2. 2 times this is x. 2 times y is 2y. And 2 times negative 3 is negative 6. There's your standard form. You could write a 1 if you want. 1x plus 2y. Doesn't matter. All right. Quadratic. I gave you a pretty easy quadratic problem. I should have put a vertex a little differently. X-intercepts. There's only one. And if you've been practicing your bounce back stuff recently, then you know that this thing has a multiplicity of 2 right there. You remember that? So we can put this is 2, 0. And you can also put this has a multiplicity of 2. Maybe that'll help you a little bit. Maybe that'll make you understand, really, that you know what your equation should kind of look like, even in vertex form. Not just factored form. In fact, factored and vertex are the same thing for this one. Your y-intercept is right there. That's 0, 4. Okay, your vertex form. Here's what vertex form looks like. Wow. Okay, your vertex is also the same as your x-intercept. It's at 2, 0. Again, that's why I kind of felt bad doing this problem like this. Your stretch factor, there are a lot of different ways you can do it. Maybe you remember this. 1, 1, 2, 4. It's a standard positive stretch factor of 1. This is y equals 1 times x minus h squared plus k. Your k is 0. Do we really need that written? Nah. There it is. Like I said, I gave you a pretty simple one there. Should have went for even just down here for a vertex. I should have changed that. Okay, let's distribute that FOIL. That's x squared minus 2x minus 2x plus 4. So you get y equals x squared minus 4x plus 4. There you go. Standard form. Okay, 2 more problems and we're done. X-intercepts right here. I got negative 4, 0, 0, 0, and 4, 0. So this is definitely at least a cubic function. This also could be a quintic. It could be a, I don't know what they're called after that. It could be power of 7. That's why I just said write polynomial equations. I didn't say with this certain stretch factor, with these ones. I didn't say with a certain stretch factor. I didn't say knowing that it's a cubic. Now I know it's not a quartic. It starts from the bottom, finishes at top. I definitely know it's not quadratic or linear. So you got to go with what you know. That's all. Y-intercept is 0, 0, passes through the origin. Okay, factored form. You write some stuff here. Make sure that you understand that these x-intercepts mean x equals negative 4, x equals 0, x equals positive 4. So you have x plus 4 as a factor, x plus 0 or x, and x minus 4. These are your factors in factored form here. Remember, we're working backwards from your other problems, and if you have trouble with it, go to your previous problems and look at what you had. You went from factored form to your solutions. Now we're going from solutions to factored form. See how they translate. You can always look at different problems and have them help you if you need to. So this is going to be y equals x times x plus 4 times x minus 4, which is a cubic. Now here's another thing about it that you have to be careful of. This was positive. To make sure you know it's positive there. I mean, I think you'll not think about that, so you're going to leave it positive. But make sure it's not negative first before you go. Okay, standard form. I gave you some room to work here. It's better to do this stuff first because there might be more recognizable qualities with them. You've done a lot of quadratics like this before, or foiling. So this will be x times, this is a difference of 2 squares. This is x squared minus 16. See, worked out pretty well. Distribute the x, you get y equals x cubed minus 16x. Good to go, aren't we? There we go. Okay, one more problem and that's it. I'm done. Okay, x-intercepts. Negative 3, 0, 0, 0, and 2, 0. Y-intercept 0, 0. Now you might be saying, especially if you already did this, you might be going like, Mr. Robinson, you went too quickly through this. Are you assuming this is a cubic function because it passes through 3 times? Absolutely not, guys. Let's look at that a little bit closer. Well, I'm not going to zoom in, but let's erase that. What happened here? That's a bounce back. That is a bounce back. Bounce back. So I want you to think of the fact that it's a squared function, perhaps, or to the 4th power, or whatever else. As far as you know, it has a multiplicity of 2, at least. So 2, 0, mult of 2. Even if you didn't know that, is this a cubic? It starts down, stays down, and that's another important part about this thing. This is what makes this a challenge. The bounce back starts down, stays down. And then obviously you have to do some more multiplication here. Factored form. So what do you have here? First of all, no constant value. And you might have noticed I shouldn't have a constant value here. My y-intercept was 0. I should have plus 0 at the end. So if you screwed up somewhere, double check that. Shouldn't have a constant. I shouldn't have a constant at the end of this either. Okay. X is one of my numbers, 0, 0. X plus 3 for negative 3, 0. And x minus 2 for my 2, 0. Now, how's a multiplicity of 2? So you want to square that puppy. There we go. Okay, x minus 2 quantity squared. This looks like a quartic. 1, 2, 3, 4. Now, am I missing anything? Remember what I said about starts down, stays down. The natural behavior of a quartic is starts up, stays up. That's when your leading term is positive. So in factored form, you know that there's a negative lurking out there somewhere that you have to take care of so that your quartic will be negative. I have to put a negative right here. That's a negative, not even necessarily a negative x, but there's a negative that exists in your factoring. So here's what I'll do. I'll leave the negative x out there. I'll even leave the x plus 3 right there. Let's do x minus 2 quantity squared. We just did that up here. X squared minus 4x plus 4. All right. X plus 3 with x squared minus 4x plus 4. For the sake of, I haven't done this in a while, let's do that grid and put in all these values and then combine them. X plus 3, x squared minus 4x and 4. You get x cubed, negative 4x squared. A lot of people like to do it this way. I'm not going to deprive them of that, absolutely not. And I'll exercise this option every so often. I should probably do it this way more. I'm kind of against the don't do visuals unless you understand them, which, I understand what these things are. But, I don't know. To me, they always became gimmicks. It's like somebody said, let's make it easier because we say it is. Is it easier? Maybe. Some people can't visualize the other way. Or, they forget negatives and stuff. So there are definitely benefits to this way. All right, I have to distribute a negative x here. So your final answer, last thing so I can breathe again. Plus 8x squared minus 12x. And there you go. There's your standard form. And negative x to the fourth. It was a quartic. I expected a quartic out of that. So remember, this was linear, quadratic, cubic, and quartic. Okay, that was it. There's your practice test. And the explanations, remember, this wasn't just teaching you the stuff. This was also, how do you take a test? How do you talk about the stuff in your head? I think that's super important as you do the stuff. So take that to heart, please. Ask questions as needed, but I hope that this exhausted this stuff plenty enough that you kind of know what to do here. Okay, so I'm gonna, and one last thing. Apparently I do shout-outs now. I got to do a shout-out to Ashley in 7th period. Okay, so maybe I'll do shout-outs at the beginning from now on. All right, I think I made it under an hour and a half, under 90. Good to go without those notes. I'm gonna see if I can put up a long division video. I made one, but I don't really like the result of it. So we'll see if I end up putting that up or not. So best of luck to y'all.